A wind turbine is a sophisticated system of components that must all work together to efficiently produce power. Like most sophisticated systems, it can be divided into sections. Some sections are dedicated to capturing the wind energy. Other sections convert the mechanical kinetic energy into electrical energy. All of the sections depend on a control system to keep the turbine facing into the wind and turning at the proper rate. Let's look at the parts of a wind turbine's closed-loop control system. A closed-loop control system measures variables that affect system performance and compares those measurements to the desired performance, which is called the set point. A turbine's yaw system control measures wind direction, wind speed, and the current position of the turbine. Measurements of these variables are made using sensors. A sensor is a device that converts a physical quantity, such as wind speed or direction, into an electrical signal, such as voltage, current, or frequency, that can be understood by the controller. Information from the sensors is called feedback. Feedback is used by the controller to make decisions and take action to keep the wind turbine system operating. Controllers follow programmed instructions to keep the turbine running smoothly. An important control function is to keep the turbine pointed into the wind. So a simple instruction might be, if the wind direction differs from the direction the turbine is pointing by more than 5 degrees, then turn the nacelle until it is aligned. In this case, a turbine aligned with the wind is the set point. To maintain it, the controller receives a signal from the wind directional vane and compares it to the signal from the nacelle position sensor. If the wind direction and nacelle position are the same, no action is required, and the nacelle remains locked in its current position. When the wind direction changes, there is a difference between the set point and the nacelle position, and an error signal is produced. The error signal is used by the controller to produce a correction signal that will set actuators in motion to move the nacelle to the set point. Actuators are devices such as electric motors or hydraulic cylinders that create motion and can be controlled with an electrical signal. The controller turns them on in order to bring the system back to the set point, and then it shuts them off until the next error occurs. Let's look more closely at the yaw control system. There are 3 common reasons for the system to yaw or rotate the nacelle. The first is to point the nacelle into the wind for power generation. The second is to detect cable twist resulting from yaw activity and unwind the cables as necessary. Finally, it may be necessary to turn the nacelle away from the wind. This is called furling, and it is used to protect the turbine from high winds or to stop hub rotation for shutdown. During normal operation, when the wind speed is above 3 to 4 meters per second, the controller will keep the nacelle pointed into the wind and make corrections as the wind changes direction. During times of low or no wind, it is not necessary to keep the nacelle pointing into the wind. In fact, tracking a wind that is too low to produce power results in unnecessary wear on the yaw system. As the nacelle tracks the wind, the flexible power cables become twisted, but might untwist as the wind changes direction. Sensors detect nacelle rotation, and the controller counts the revolutions. If the twist becomes excessive, the controller will put the turbine into a stop state and rotate the nacelle to untwist the cables. If the nacelle is pointing 180 degrees away from the wind, the controller will determine which direction will untwist the cables and then turn the nacelle in that direction to realign it with the wind. In the next section, we'll look at the sensors used in a typical yaw control system.